Hello, I'm Christina Aston from Physics Partners, and in this short film we're going to have a look at how to teach radioactivity. The film is part of a series to help you with your physics teaching, whether you're new to physics, new to teaching, or just looking for some new ideas. I'll focus especially on the misconceptions that students have and give you some tips for getting the main ideas across. So feel free to pause, take notes, rewind, or watch again. Students often get confused between the properties of alpha, beta and gamma radiation, and they can have difficulties writing balanced nuclear equations. Irradiation and contamination and also half-life can present difficulties, but we'll deal with those in another film. So this topic leads on nicely from teaching about atomic structure, and it's really important that students know how to work out how many particles are present in an atom from looking at the data on a periodic table. For example, 14,6 carbon here has 14 nucleons. These are the protons and neutrons that inhabit the nucleus, 6 of which are protons, and the protons are what make this a carbon atom, whereas the neutron number is variable and gives rise to different isotopes. Here we've got 8 neutrons. Here's what beryllium looks like on the periodic table. It has about 9 nucleons, 4 of which are protons and therefore 5 are neutrons. But in fact the nucleon number is slightly over 9 because beryllium has several possible isotopes, each with a different number of neutrons, and the average is 5.0122. Lots of practice on this is really worth an investment at this stage, and here's a website where your students can do just that. And this simulation from the wonderful PhET website is also brilliant. Here I'm building a lithium atom, and you can see that it starts off unstable until I add the requisite number of neutrons and then the electrons to stop it being an ion and to turn it into a stable atom. This table will really help students to understand the differences between alpha, beta and gamma, the 3 main types of radioactivity that they'll meet at GCSE. You can pause the film here to fill it in yourself, and we'll come back to it later. Make it clear to the students that radioactive isotopes are radioactive because they are unstable. That is, that they have an imbalance of protons or neutrons in the nucleus. And they can become more stable by emitting alpha, beta or gamma from the nucleus. This is what we call radioactivity. It's a special type of radiation, but it comes spontaneously from the nucleus. It's really important that the students have an understanding of what's going on in the nucleus. This will help them to remember the properties of alpha, beta and gamma. Some nuclei have too many protons to be stable. They emit alpha particles, 2 protons and 2 neutrons, in other words a helium nucleus. It's therefore denoted as 4,2 helium, as it's made up of 4 nucleons, 2 of which are protons, or 4,2 alpha. The 2 protons make this positively charged, a charge of +2. It's heavy and slow, relatively speaking, crashing through matter rather like a bowling ball, causing lots of ionisation because of its charge. So the parent decay results in a new daughter nucleus being created, containing a different number of protons and neutrons, and because the proton number has changed, an atom of a different chemical element is created. Beta, or strictly speaking beta minus particles, are electrons. Now this should surprise your students because electrons are not normally found in the nucleus. What's going on here is that a neutron is spontaneously turning into a proton, an electron, and a tiny piece of antimatter called an antineutrino, which we usually ignore at this level. The electron is spat out of the nucleus as the high-speed beta particle. We denote it as 0 - 1 e, or beta. So this happens when the nucleus has too many neutrons, causing it to be unstable. Beta particles are fast, light and with a charge of just -1, and therefore they're not as ionising as alpha particles. Beta plus decay is sometimes introduced here. A beta plus particle, also called a positron, is the antimatter equivalent of an electron, and it's positively charged. Basically, it's like a positive electron. And this is written as 0 + 1 e. A gamma ray is a burst of energy emitted by some unstable nuclei, often those that have just given out an alpha or beta particle as the remaining nucleons sort of rearrange themselves. Students should recognise this as a high energy electromagnetic wave. Other types of decay, such as neutron emission, are also possible. So alpha and beta decay both involve emitting particles, and the resulting daughter nucleus is now a different element. This is called transmutation. If you have radioactive sources at your school, this is the time to demonstrate them, but do speak to your school radiation protection supervisor before handling them. You can demonstrate how far the radioactivity from each source penetrates through air, or what absorber will stop them. Alpha particles are stopped easily because they are highly ionising due to their charge and mass. Gamma rays are the opposite, with no charge or mass, and beta particles are somewhere in between. This virtual lab is a great way to show the penetrating power of the 3 different types of radioactivity, especially if you don't have your own sources at school. And exploring it will really help students to appreciate the different properties of alpha, beta and gamma. Let's have a look at the table I showed you earlier. You can pause the film to check your answers. I want to point out that the ionising power is related to the charge and mass, and in turn has an effect on the range and penetrating power. Okay, let's look at balancing nuclear equations now. Very simply, the numbers on the top have to balance on both sides of the equation, that's the nucleon numbers, as do the numbers on the bottom, the proton numbers. The trick is to remember how to write the alpha or beta particle. So we're told that AM241, that's americium, you'll find this in smoke detectors, is an alpha emitter. So we write 42 alpha or 42He for helium on this side, and then figure out what must be left. So the AM nucleus has lost 4 nucleons, so 241 minus 4 leaves 237, and it's lost 2 protons, so 95 minus 2 leaves 93. And we look up on the periodic table which element has 93 protons, which element is number 93, and it's neptunium. In this example, we're starting with 14,6 carbon. It's a radioactive isotope of carbon that we use for carbon dating, and we're told it's a beta emitter. So on this side we write the beta particle, which is 0 minus 1 beta, or we can write an E here. And we must be careful of the minus sign. Top numbers, well, nothing's changed. 14 remains as 14, but on the bottom number, the proton number needs to go up by 1. So that's 7. 7 minus 1 makes 6. And element number 7 is nitrogen. Here are some nuclear equations you can try for yourself. Just remember always to make sure that the top numbers balance on each side of the equation and the bottom numbers. And remember that if you've got alpha or beta decay, the right-hand side will show a new nucleus because transmutation has occurred. Very often the daughter product is also radioactive and it self-decays, and this can give rise to a whole series of decays like this one here, each with its own half-life, before we eventually end up with a stable end product. And there'll be more on half-life in another film. Well, I hope that's helped to give your students a deeper understanding of this topic rather than just relying on surface recall. Underneath the film, you'll find links to some of the resources I've shared, which I hope are useful. Look forward to seeing you again soon.